We are going to talk about Kotlin and Kotlin 2.0, and before that, I would love to have a small poll. So, how many people here are using Kotlin? And that's nice, really nice. And how many people are using Kotlin 2.0? Okay, so still not that many. So today I'm going to talk about Kotlin 2.0, about its changes, and about future directions of Kotlin. So again, welcome everyone. My name is Michail Zarečenskij. I am in charge of language design and Kotlin. And we'll begin with a brief recap of past changes in Kotlin and reasons for the K2 compiler or Kotlin 2.0 compiler. Then I'll highlight the main changes of 2.0, and then we'll be looking at the new exciting features that we'll be able to ship after Kotlin 2.0. And I would love to start with a short overview of Kotlin and its history, as it's hard to really talk about the present and future without mentioning the past. So the first thing that I'd like to mention is that the first version of Kotlin was released about 8 years ago, and a lot of things have changed since then. And considering language features after 2.0 alone, it's worth mentioning coroutines, functional interfaces, multi-platform projects, type aliases, contracts, and many others. And it might seem like these features have been with Kotlin since day one, but they were actually introduced gradually. And a closer look at the changes reveals such features as trailing commas, range until operator, exhaustive when statements. And if you look even closer, you can see that over past years, the Kotlin programming language has evolved pretty significantly. And Kotlin updates has resulted in the addition of several dozen features, not mentioning bug fixes, smartcast, and type inference improvements. So if we consider these updates, can we say that Kotlin is mostly about a language? Of course, we can to some extent. Kotlin is a language, but of course not only. Like, apart from the core language, Kotlin targets several compilation environments, including JVM, native, Wasm. We also offer Kotlin scripting with its shiny Gradle Kotlin DSL, so where you can write Gradle scripts and have all advantages of static typing and Kotlin. We know that Kotlin is extensively used for Android and server-side development. It has all the necessary technological stack to develop, debug, and publish applications. Of course, we develop plugins for IntelliJ IDEA and Fleet, provide a range of our own libraries, and have like thousands of open source libraries from our community. And also, Kotlin offers somewhat unique capabilities via compiler plugins, allowing for adoption for new styles and frameworks. And of course, one of the main examples here is that we have this Compose, Jetpack Compose, a toolkit for building UI declaratively. And here's the new Kotlin compiler. So for those people who don't know that, we basically rewrote the whole front-end part of the Kotlin compiler in 2.0, which was released a month ago. And it took us actually about 5 years to achieve this. And a very rational question is, why did we rewrite the compiler if we could achieve all of that? And the first thing is that some of Kotlin language features and directions have appeared quite unexpectedly. The compiler wasn't ready for specific requirements. And in general, that's okay, because we can't predict the future or know which language features will be needed in 5 or 10 years. But some features require slightly different compiler architecture. Specifically, our multi-platform capabilities require non-trivial contracts from the compiler to unify the work across multiple targets while managing both common code and platform code. And now that we have this vision for multi-platform projects, we want to double down on this direction, and we need a solid foundation in our core compiler. The next issue concerns our interaction with compiler plugins and IDEs. So originally, the compiler was developed in the same repository as the plugin for IntelliJ IDEA, resulting in tight integration with our IDE and utilizing all the necessary internal API of the compiler. And this allowed us for rapid development, but came with its own costs. And one of them is that we didn't have a reasonable compiler API. And people used to come to us and ask us, like, where's the compiler API? And it's not that we hid it. There was just no compiler API at all, just a bunch of internals. And now with more tooling around Kotlin, it has become difficult to maintain and make changes to the compiler and to write more extensions. And as part of this work, we also moved the plugin for IntelliJ IDEA to the Kotlin, from the Kotlin monorepo to IntelliJ IDEA, and introduced an API layer to communicate with the compiler. And now this API layer can be used for compiler plugins, KSP, static analysis tools, basically every tool that has some semantic information, that requires some semantic information about your code. And once again, providing opportunities to write compiler extensions for the JVM is one thing, but offering support for multi-platform compiler plugins is a whole different story. And of course, there is compilation time performance. We can never be truly satisfied with the performance, especially with the growing lines of code and extensions for Kotlin. And here's Kotlin 2.0 with all these ideas and foundations in mind. So Kotlin 2.0 was released a month ago, and the update includes more than 80 features across different subsystems, including build tools, incremental compilation, Kotlin backends, and so on. But one of the most significant aspects of Kotlin 2.0 is its focus on performance and correctness. And however, as it usually happens when you're rewriting something, you end up with a bunch of new features. But in our case, all of these features are not syntactical, as we'll see, but more about extending our existing features in Kotlin, making them more powerful and flexible. And as one of the results, we don't have large breaking changes in this release. So in other words, there are more than 100 features in this release, but none of them are syntactical. So how can we describe compiler changes in general? One of the key changes of the compiler is the introduction of the front-end intermediate representation, or FIR. This is a transformative change that deconstructs complex language constructs into simpler, more manageable ones. So this so-called desugaring in Kotlin compilation happens way earlier than before, allowing us to have more consistent rules for analysis. Next, we introduced a phased approach to its analysis process. With this approach, it's possible to provide specific points for integrating additional functionality into the compiler and IDE. And now the compiler will be aware of such changes. And a key benefit here is that if you develop a compiler plugin, you don't need to provide a separate IDE plugin anymore for highlighting and having auto-completion for new symbols that are generated by such a compiler plugin. With the current architecture, our IDE will automatically recognize new compiler extensions and will properly highlight these new constructions. And last but not least, we rewrote our control flow engine, which is designed to offer a more sophisticated analysis of code's execution path. So with this engine, the compiler can better detect unreachable code, potential bugs, and other issues that could affect the runtime behavior of applications. And this is also where most of our new features come from. So, but what are user-visible changes? I'm going to highlight just a few, so let's start one by one. So, front-end intermediate representation. So, one of the good things about Kotlin, and actually indeed any other powerful language, is their ability to compose different language constructs together. For example, Kotlin has many operators designed to work together, although the compiler implementation might not always align with your expectations. And to give you some intuition, we can start with this very simple code. Here we have a simple function that increments the first element of the mutable list of longs by adding an integer literal 1. Note that we are adding the first element of a list, which is long, with a literal 1. So here we used a numeric conversion from an integer literal to a long. So now let's try to simplify this thing using plus assign operator. If we do this, the compiler will emit an error because it failed to combine operator calls and numeric conversion somewhere, and we could meet such issues from time to time. If we try to deconstruct this thing, we can actually see that we used 3 different operators here. It's set, get and plus, as well as a numeric conversion. And previously, the compiler failed to desugar this expression properly by losing this conversion during the process somewhere. And in Kotlin 2.0, we fixed this by fundamentally rewriting how the compiler handles these cases. And while this particular case is simple, it can be extended to more conversions such as suspend ones or conversions that involve SAMs, like single abstract method conversions, and so on. And these cases can be even more complicated. So for example, here we have the class box that holds our mutable list of longs. And in the function, we want to increment the first element of the list again. And the 1.9 compiler fails to do so, but for a slightly different reason, which is related to using a nullable left-hand side of a plus assign operator. And in 2.0, such expression can be properly desugared, adding even more operators to the desugaring process without losing other properties of the language. So again, Kotlin's power comes from its composability. And with Kotlin 2.0, we have more consistent and robust rules for operators, delegated properties, extension functions, and their combinations. And let's get back to other features. The next big thing is our new control flow engine that helps us to predict the code behavior. Or in terms of Kotlin, it means that we'll get more smart casts. So let's see a few particular examples. So this is a very common code. We have the class cat with a single method, and in the function, that animal will check. If our object is a cat, then we can safely invoke its method. Pretty straightforward. One missing piece here is that if we extract the nullability check to a variable, then we'll get an error that we can't call the method anymore. And the reason is that our variables don't contribute to the smart cast logic. Only a few expressions did, like type checks or null checks. And with Kotlin 2.0, local variables can carry the necessary data flow information as well, and also contribute to smart casts. So in the example above, our code will compile just fine. And speaking about composability, the feature works with all regular smart casts, including contracts. So in the example, we have a class card with a property holder of a nullable string type. And in our variable card with holder, now can produce two smart casts. The first smart cast is from the type check, and the second one is from the function is null or empty. And they both will be applied in appropriate blocks of code. So our initial parameter of the type any can be transformed into string without any explicit casts. The next change is about smart casts inside changing closures of lambdas. So if you take a look at this function index of max, we can see that it returns the index of the maximum element in an int array. And if the array is empty, it returns null. And the interesting part for us is actually this check for null. You see, this check didn't produce any smart cast for the next max I variable because the variable is captured inside the lambda. And in general, we don't know anything about this lambda. It could be stored somewhere and be invoked later, even after the for each index call. And because the variable max I is captured, or in other words, it was defined outside of the lambda, such a variable could be assigned to null somewhere else as well. So all in all, this behavior could affect the smart cast, and it cannot be stable. But one thing we take advantage of, and it's for each index function. You know that this function is actually an inline one. So it means that its body has to be inlined at a call site, and its lambda cannot be stored anywhere and has to be executed in place. And in Kotlin, we have a special mechanism in the language to express this, which is part of our effect system or contract system. So starting from Kotlin 2.0, the compiler treats all inline functions as having an implicit call-in-place contract, explicitly telling the compiler that such lambdas cannot be stored anywhere. And this allows us for more smart casts, including smart casts inside changing closures. So now in Kotlin 2.0, we can prove that such smart casts are safe, and we can apply them for captured values as well. The next simple update is about SmartCast after a logical OR operator. So let's have a simple interface status that has a function signal and 3 sub-interfaces, OK, postponed, and declined. Previously, the compiler didn't perform any SmartCasts after a logical OR operator at all. So if we checked that our variable is either postponed or declined, we still couldn't invoke the function signal. And with the K2 compiler, we start to merge information from the OR operator. And now we can infer that our variable is the closest supertype of postponed or declined types, which is status. Therefore, we can invoke the function signal. Again, before, only simple type checks and casts contributed to SmartCasts, but now we extended such expressions to include local variables and also OR operator. And there are just more bug fixes to SmartCast mechanics. Some of them are small improvements, some are bug fixes in the language, but in general, the static analysis of the compiler has significantly improved in Kotlin 2.0. And what's next after 2.0? So Kotlin, as we saw, is more than just a language, and we have a lot of exciting things planned. So we are moving towards multi-platform development with Swift export, a stable key format, Kotlin native improvements. We are also focusing on tooling, including Ampere, our new experimental build tool, improvements to the Kotlin Gradle plugin notebooks, build reports, and so on. Additionally, we continue enhancing our call libraries, making the WASM target stable, and improving Java interop. But today, I will cover just a small part of our future plans, giving you a glimpse of what's ahead of the language. And the first thing that I would like to talk about is about data flow framework. So we've seen quite a few changes to SmartCasts. And we believe that describing control flow is one of the main tasks of a developer. And we are working with data more and more, and we like to provide a more concise syntax to inspect and describe conditions. And this improves readability of the code, which is usually more important than writing code because we read code way more often than we write it. And in many cases, it also removes layers of nesting. And for example, we can see that, for example, Java has included switch expression and pattern matching on records. And although Kotlin has included some of these features, like when expressions, and it's at forefront in many others with the notion of SmartCasts or flow typing, we also should keep improving to give our users even more powerful tools to express the control flow. And SmartCasts are among the most efficient methods to enhance data-oriented features, as we see. So because they don't require any additional language constructs, no additional syntax, and so on. And they can be improved incrementally, as demonstrated with the K2 compiler. But we are also working on a number of other features as well. And here's the first direction where we are going to provide more and more updates after Kotlin 2.0. And this direction is about data recognition and deconstruction. And it includes such features as guards, or pattern matching without the notion of binding, context-sensitive resolution, data class improvements, generalized ADTs, and effect system capabilities. So let's dive into this direction in more detail. Let's take some code. So we'll be using this example, so I'll go through it. This Kotlin code defines a composable function designed for use in UI. It takes a sequence of data and an ID string as parameters. And within a lazy column, it finds the last data object matching the given ID. Then, based on the type of selected search panel, it conditionally displays different UI elements. If the panel is a news panel and not blocked, it displays a news result with the found date. You see, we repeated the search panel variable 4 times within the when expression. And this repetition usually suggests that such a value is central to deciding which UI component to render. However, repeating the variable multiple times could potentially make the code less concise and slightly harder to refactor in the future, as the variable search panel was intended to use only in when statement. And in Kotlin, one way to address this might involve leveraging so-called when-with-subject construction, where the subject, search panel in our case, is captured and restricted to the body of this when. So let's try doing this. If we do this, we immediately get a compilation error that end is forbidden at this position. And the reason is that when expression in Kotlin allows for type checking or matching against specific values only. And to mitigate this aspect, we are going to introduce guard conditions in when. So the essence of adding guard conditions is to allow for more nuanced checks within when expressions, without significant changes to the language syntax. Guard clauses, if an example, allow for additional conditions to be checked along with the type check before executing the branch's code, reducing the need for nested if statements or verbose when branches. But can we do better? You see, we still have to repeat search panel for each branch. That makes the code more verbose than necessary. And we still have to parse through redundant information. So it also contributes to the all things that's related to reading code. And so the next little improvement will allow handling through instances of seal types or enum entries directly, without repeating the base class name when the expected type is well known. So this approach reduces the need to repeat search panel, making the code cleaner and more focused on the unique handling of each panel type. And the feature is also applicable to all the places where the expected type is well known. One such place is the addition of default values of parameters. So here we repeated status a few times, and with context-sensitive resolution, it will be possible to omit status on the right. And so for those who are familiar with Swift, you probably know about that similar feature, which is also probably called context-sensitive resolution, but it actually, the feature in Swift is way more powerful and also brings exponential resolution to the language. So, and in our case, it's way more simpler. So we are going to allow context-sensitive resolution only for the cases where the expected type is well known. And as one of the limitations, it won't work in position of arguments. So the next thing is JDT smartcasts. And here we have a small terminology problem because JDT stands for generalized algebraic data types. And in Kotlin, we don't use this term. So this term actually comes from functional languages and type theory with algebraic data types, which usually refer to sum types and product types. And in Kotlin and in most in major production languages, people use seal types and data classes instead. I'm still going to use JDT abbreviation, but keep in mind that we actually don't have this term in Kotlin. We are not that functional. So what's all about? So this Kotlin code defines a seal class container which holds a value of a generic type T. And also we have int container, which is a subclass and contains an int value initialized to 42. And string container, which is a subclass and contains a string value initialized to Kotlin. If we write this simple function unbox, we know that we can, which is generic and returns just a value a, we can easily write container.value and everything will work. But if we do the same operation for subclasses, we'll get a compilation error, which might be surprising at first sight. But let's take a closer look. We actually can see that we promised to return a value of type A, but we are actually returning either string or int, which is forbidden. And if we inline those values, it will be even more clear that this code is non-trivial, because here we have to somehow bind our generic type A to either string or to int. So that's actually non-trivial for the compiler. But we definitely know that at runtime, this is perfectly fine. There can be no any other values. And this is all about JDT style smartcasts, which means that we use subclassing information to convince our compiler that this generic A can be either int or string after these type checks. And the topic is currently under research, but we see pretty good results, and we are going to publish a detailed KIP with a proposal soon. The next thing that concerns many users is about lack of name-based destructuring. So right now we know that if we have a data class, we can destructure and use any names at call site. For example, here we have a mistake, for example, and because we used different names, which can affect the logic of the following code. And this is something that we would like to migrate from, and starting in Kotlin 2.2, we'll start emitting ID warnings and the warnings at the compiler that surname, for example, doesn't match the property name, or first name doesn't match the property last name. And ultimately, we would love to get rid of our component functions from data classes as well. So that will also result in less compiler ABI. And also to make the migration more smoother, we are going to introduce special syntax to assign new names for destructuring properties. And that was about direction that we called data recognition and deconstruction. So again, we are going to introduce guards, which are going to beta in Kotlin 2.0, Kotlin 2.1, context-sensitive resolution in Kotlin 2.2, generalized ADTs, data classes improvements with first results in Kotlin 2.1. And also, I have this item about effect system capabilities. I'm not going to talk about this today because it will require a few lectures, but we are going to improve these capabilities in each release. But let's return to our original example. We still have a couple interesting functions there, and one of them is lazy column function. If we take a look at the lazy column function, we can see that it's a composable function provided by the Compose UI toolkit and used to display a scrollable list of items that are lazily loaded. And as many UI dedicated functions, it has a lot of parameters that carry rendering information. And such functions heavily utilize the use of parameters with default values that allow us to reduce the number of required overloads. But what if we decide to add a new parameter to such a function? In this case, we'll have to add it to a new overload to maintain backwards compatibility. And these are just a few examples where authors had to add new overloads and deprecate previous version of a function. But let's break it down. So what actually happens here? And for example, we have a simple function foo that has only one parameter. And if we, on JVM, we know that this function will be compiled to like public final static void and many other words function foo that has a single parameter int. So that's pretty straightforward. And now, for example, if we add a new parameter with a default value, what is going to be generated? First, we are going to have a straightforward implementation, which also takes two parameters. And also, we'll have this synthetic method that takes two parameters and a mask. And if we decompile this function, this second function, it will look like this. So it's actually compiled to something like that. So they have our first two parameters from the original signature, mask, and also a marker, which is used for Kotlin compiler to avoid some hackers. And in the body, we can check that if our mask tells us which default parameters were used at call site, and for example, if nothing has been passed, then we can use this default value and then delegate to our original function. So the problem here is that we have those two functions, but we don't have a function with a single int. So it means that adding a new value that has a default value will break existing libraries that depend actually on the function that has only one parameter. And the problem is that there are no good compilation strategies that could avoid this. So we can't just generate all of the functions with, for example, with many parameters for each of them, because it will be resulted in many additional methods, and it will be like an exponential. It will bring a lot of new methods, and that's why we want to solve it on a language level, because it also, so right now people have to add new overload, which means also that they have to duplicate all the documentation for all the parameters, and which, as we saw, is a lot. So what we are going to do is that if we inspect such functions, we can notice that many parameters are just settings that are shared between similar UI components. And we propose a solution that follows the idea of having a class to represent the arguments. And this proposal provides a way to design API with a growing number of optional arguments, keeping source compatibility, and also aiming to keep binary compatibility as much as possible. And also, parameters are documented only once at this data arg class. And of course, we want to leave the door open for library authors to have full control over the representation of arguments by skipping explicit creation of such classes at call sites. And it was one of the features dedicated to the area of library code evolution. And in this area, we are also working on signature management, features aiming at providing mechanisms to enforce name parameters or check for return values. And of course, we have a lot of that regarding kdoc. But we still have one interesting function in our example, and it's the function last from the Kotlin standards library. The function last iterates over each element in the sequence, and for each element, it checks. If the element matches the predicate, it updates the variable result to that element. This means only the last matching element will be stored in result by the end of the iteration. Right? Actually, no, but because the predicate can check for nulls. And you see, our connection can store nulls, and we can differentiate the situation when we didn't find anything from the situation when we found null. And to handle these cases, we need an additional variable found that will be updated if we actually found the required element. So this solution also comes with the price of more complicated code and an unchecked cast at the end. And for example, in order to get rid of this additional Boolean variable, we could use some private object as a tag that will serve as a signal if we didn't find anything in the sequence. But is this approach good enough? Well, not really, because in this case, we also have to convince our type system by using the most generic type any, and we still have this unchecked cast at the end. So this code clearly shows that something is missing in our type system. And the missing part is the ability to specify union types for errors and exceptions. So the code uses a union type for the result variable. Union types allow a variable to hold a value of one type or another. And in this case, either an element of the sequence or a special not found object. So note that in this case, the type system immediately helps us to streamline the code by putting automatic smart casts where it's needed. And this pattern with unions is designed specifically to handle error situations and distinguish between successful and error cases. And I have to mention that we are not going to add full-blown unions to the language. These kind of unions are designed specifically to handle error situations, because union types in their full form bring an undecidable problem for a type checker and can badly affect the performance of the compiler. And also, we are looking how we could extend union types for other positions, namely for return types, and parameter types, and how we can use special operators in chain calls to collect, for example, all the errors into one type when we have a few invocations of functions that return exceptions. And that part was about increasing abstraction, which also includes such features as context parameters that were experimental in Kotlin since, I think, Kotlin 1.8, and we are moving them to beta in Kotlin 2.2. Union types for errors, string literals and string interpolation, and of course, deep immutability. So we still hope that Valhalla will come to the JVM world and will get value classes, and together with value classes, we need some sort of mechanism to mutate those classes, because they will be immutable by default. And we see a few cases and few solutions to that, how we can bring convenient updates for such structures in future. And also explicit backing fields. So this is something that is pretty familiar for Android developers, that you usually have to use this pattern, which is called implicit backing field, where you have a private val with _city, and then you have like a public city, which is just a read-only, because you want to expose only the read-only part of it. And you have to write and duplicate this city 3 times, which is basically the same thing semantically. And if you check, for example, GitHub and open source repositories, we can see that this pattern occurs in more than 100,000 files. And usually it's a pair of list and mutable list, shared flow to mutable shared flow, live data to mutable live data, and so on. So that's actually a good candidate for a language feature. And we'd like to introduce explicit field feature, which will encapsulate the immutable part in the main property of, for example, here in the property city. And that's actually it from my side for today. We still have a few minutes for questions. So thank you all.